The towering white cliffs that line the south coast of England have a fascinating story to tell about our planet's ancient past. Though they appear as an imposing monolithic mass from a distance, these chalk cliffs are actually made up of countless microscopic layers built over millions of years. To decode this chalky record, we must look to the heavens above.
Life on Earth began about 3 billion years ago. The young Earth was a fiery place with a poisonous atmosphere, and it was being hit by meteorites. But gradually everything calmed down, and what happened was that we had rain for centuries and it formed the seas. But it was very small, about the size of bacteria.
On and on we go. On and on we go, on and on we go, we go. Life is a step in time, keeps on moving along that line beyond the boundaries of solitude, a place for storing memories.
Then nothing visibly happened very much, although a lot was going on in the micro world. About 1,000 million years ago, we get the first collections of cells. Green algae, for example. Then we have a major event, a mere 550 million years ago, when we get bilateral symmetry. I bet you're wondering what that is. Look at your face in the mirror. You have 2 nostrils, 2 eyes, 2 ears. That is bilateral symmetry. So far, everything was going on in the sea. Then about just over 400 million years ago, we get the first land plants colonizing the continents. And as a result of that, the animals can move out onto the land. A mere 200 million years ago, we get the beginnings of the dinosaurs. So far, everything was going on in the sea. Life began in the seas. The early seas were a chemical experiment. You had organic compounds, and for about 1,000 million years, possibly with a bit of help from outer space, they gradually formed as organisms as complicated as a bacterium. Then came along cells, and the cells were combined to form more complex organisms, like, for example, millipedes, which are so advanced they even have a skeleton, legs and a head. They are perfectly good bilateria. And it's animals like that that would have been ready to colonize the land as soon as the plants got onto the land in order to provide them a natural habitat. 85 million years ago, where the story of Seaford starts, it was under the sea. At the bottom of the sea was a white ooze accumulated. We now call that chalk. Over the millions of years, this ooze was compressed to form a rock, which was then raised to form the cliffs and our familiar landscape. Water temperature would have been at least 10 degrees warmer than it is today, and the seas contain some very strange animals, like marine lizards and ammonites. It was a very unfamiliar world. It was composed of a soft, white, oozy material. We now call it chalk. We're at Seaford Splash Point, aptly named, because the waves can be pretty ferocious here at times. Behind me are our beautiful white cliffs, tilted layers of chalk and flint, going back 85 million years.
In cosmic dust and ancient chalk, early life began to walk beneath the layers. Time stands still, universe's silent will. We are stardust, we are trees, more than what the eye can see. Ooh, sleeping giants, cosmic awe, each grain of sand a brand new star.
Imagine this was once the bed of the sea. The white chalk are the skeletons of brown algae, microscopic organisms which bloomed in millions in the sea. The rusty brown is the work of 85 million-year-old bacteria, which produced a dark mineral which we call fool's gold, because when it's exposed to air, it tarnishes and just leaves a rusty mark like this. Once, Seaford Head extended all the way out to sea when sea level was lower. You could have walked across over to France at the height of the Ice Age.
On and on when we go. On and on we go. On and on we go. On and on we go.
Hard to imagine, but 85 million years ago, on the bottom there would have been all kinds of shellfish, and in the waters above there would have been marine lizards, predatory animals called mosasaurs, large rays and sharks, and overhead there would have been flying large pterosaurs or flying reptiles. Have you ever wondered what's at the bottom of Seaford Head? The answer is there is a giant ammonite, an extinct kind of shellfish that lived in the age of the dinosaurs, related to the modern nautilus. Unfortunately, the Seaford Head ammonite is now buried under cliff falls and sand. The animal life that lived on the seabed would have included sea urchins. Their modern relatives can still be found on the beach here today, starfish. But sea urchins don't have arms, they're more globular, and you can find those preserved in the chalk. They're one of our most famous fossils. Also, there would have been glass sponges, which contributed to the formation of Flint, but they would have been much softer, and we get very faint impressions of those too. But perhaps most spectacular of all are the occasional shark's teeth that you can find in the chalk, or even the remains of dinosaurs. Ah, I got one. Flint lasts much longer than chalk. It's very hard. And if you look carefully at the flint pebbles on this beach, it's amazing what fossils you can find with perseverance. Wow. And what we have here is the characteristic chalk sea urchin called micrasta. You can see the 5 rays on it. Basically, it's like a starfish, but a dumpy one. Ah, got one! Found is a Micrasta sea urchin. The outline of the shell of the actual sea urchin is actually quite light and fragile, and if it wasn't for the flint, it would have soon disappeared millions of years ago. And the waves are relentless. The cliffs are going back at a conservative rate of about half a metre a year. In a million years' time, Seaford will be under the sea like Dunwich. And here we have a dumpy sea urchin, which has been turned over by an ancient storm. There's the shell, eroded away by the sea. And here's a tougher one, preserved in flint off the beach. When I was at school, all I knew about chalk was that teacher used it to write dates on the blackboard, which I then had to memorise, spellings, and long and complicated equations. It's only after I left school and went to college and finally moved to the coast that I realised what an amazing substance chalk is. So, what is the chalk? Well, back at school, when we dusted the board after teacher had finished, I didn't realise at the time that the dust coming off, which made me sneeze, was actually thousands and millions of skeletons of golden algae, microscopic creatures that left their skeletons at the bottom of the sea to form the chalk. The chalk is scientifically so important that it actually gives its name to the Cretaceous period in which Tyrannosaurus rex lived. Because chalk in Latin is Creta. Cretaceous means bearing chalk. So how did this important material form? Skeletons of golden algae accumulated on the seabed in the Cretaceous period, forming a layer which would have been about the thickness of a layer of tissue each year. The ooze was originally the hard skeletons of these golden algae because it's only the hard parts that usually preserve as fossils. Soft parts are much rarer, requiring special circumstances. That's why the sea would have been full of jellyfish, for example, but we very rarely see them. There would also have been worms in the seabed. They've turned over the chalk, but again, we don't find the culprit. But we know they were there from very rare fossils. So 85 million years ago, we had these golden algal skeletons accumulating in the ooze. So much for the chalk. But you might well ask, what about the flint layers? The answer is there are other microscopic organisms called radiolaria, and their skeletons were made of the same material as sand. And these all contributed to form the flint bands. But the flint would have been impossible without the action of bacteria on the seabed, which have been lurking there for the past 3,000 million years. By now, you might well ask, how on earth do we know the Earth is millions of years old? The answer is by measuring the Earth's natural radioactivity. If you know the rate, and then you go and look at the rocks and find the decay products of the Earth's natural radioactivity and measure those very carefully, you can then back calculate to when the process began. And once you have a radiometric date, you can then apply that to other rocks which are similar, and so you know their age as well. And here we are in Peacehaven. We're now going to look for the giant ammonite that lies buried under Seaford Head but has relatives on the foreshore here. and we're going to look at the beach, which is 1.5 million years older than this cliff top. Each step down is a mere 8,000 years. So down we go. 8,000, 16, 24, 30, 36, 40, 40.
In ancient depths you made your home, spiral guardian in waters roam, and another sea coiled and free, now stone whispers of your mystery.
When the sea's finished eroding the chalk, cutting these vertical boulders behind me, the limpets scrape away afterwards, removing even more chalk. We've got one! Here it is, 84 million year old ammonite. It may not look like much because it's completely covered in barnacles which have carefully protected it for all these years.
Oh, ammonite, lost to time, your fossil shell, a paradigm. I hear your song on the windswept shore, echoes of life from long before. Oh, 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 oh.
And look at this one. This one's actually been exposed by the sea. There's only a few limpets on it and no barnacles. And look at these lines running across the animal. They're wavy, unlike in the modern pearly nautilus or in Brian the snail, which only has straight chamber walls. The chamber walls in ammonites were very frilly and almost plant-like in the pattern they produced on the shell. These animals were adapted for massive pressure changes in the chambers. Chamber walls on Brian the snail are straight. Here, these extinct ammonites, they were frilly. These animals were built to take tremendous pressure on the shell wall as they dived up and down in the deep sea. And here's a bit of ecology. Here's a fine limpet scar. You can see how they scrape out the chalk. But next to it, there's already other wildlife moving in. Look at these elongate slits. Those are the holes left by a worm. One end of the hole the current goes in, the other end of the hole the current goes out. And behind me is a wall of green algae. Seaweed, in this case. But these plants go back hundreds of millions of years, much further than the story of Seaford. But our story doesn't finish 85 million years ago. In our area, if you look carefully at the cliff tops, there's a layer you can see where the large dinosaurs died out. But the dinosaurs themselves, being land animals, would have been miles and miles away, for example in North America. The chalk in Seaford dates from the height of the age of the dinosaurs, the ancestors of Tyrannosaurus rex. Dinosaur fossils are very, very rare. But if you look at the top of our cliffs in this area, you will notice that there are sands and clays. These date from the age of mammals, from the early tertiary times, and sometimes we find the fossil plants. We're here in Newhaven because the cliffs are less steep than at Seaford. The reason being that the pebbles destined for Seaford have now conveniently piled up since 1890 in front of West Quay, which means that the cliffs are nowhere near as steep. And behind me, you can see the end of the age of the dinosaurs, the end of the age of chalk, and the beginning of the age of mammals, our age. And the grey mud here from higher up, it came down in the winter when it was a lot wetter, so I wouldn't be sitting here, is the London clay. The same stuff that you find under London today, for which the underground was driven. 55 million years ago, that would have been a sea that spread from here all the way across southern England. And continuing well into the age of mammals, we have earth movements. Briefly, the continent of Africa collided very, very slowly with Europe. By slowly, I mean as fast as your fingernails grow. But in a million years, that's about a dozen miles. As this pressure grew between Africa and Europe, up went the Alps over tens of millions of years. Whereas in the south of England, the chalk seabed was not only compressed, but tilted and raised in a great arch. Today, the remnants of that arch are the North and South Downs. After the chalk was raised above sea level, the chalk would have been eroded by rain. There would have been rivers on the downs. And it is only with the rise of the sea level after the end of the last ice age, about 12,000 years ago, that the sea started to erode the chalk again. Here at Hope Gap, which is at the seaward end of Hope Bottom, a 20,000-year-old river valley. As Africa collided with Europe, it pushed up the chalk and it was exposed to the elements which formed streams and rivers carving the valleys. But on my left is an even older feature right at the top of the cliff. That is the 100,000-year-old bank of the original River Cuckmere. And behind me is one of the most famous views in the world, the Seven Sisters. As the Ice Age ended, sea level rose, cutting back the lower ends of the valleys, leaving them high and dry. That's why we have 6 valleys and 7 hills between them, forming the Seven Sisters. The 7 White Sisters are part of Asian mythology, and people come from thousands of miles away to view this.
On and on and on and on we go. Life started millions of years ago. On and on we go. Soon we'll find that star that glows. On and on we go.
We're here in Cuckmere Haven at an exceptionally low tide. And I'm standing on grey mud, which is no ordinary grey mud. This is the bed of the ancient River Cuckmere. It's probably about 4,000 years old. And these ancient plants beginning to appear where the water's washing them out. A pair of interesting shells there. Just spotted it. We've been here many times, and now look, I've got something I haven't seen before. I'm really getting excited to go and look it up and find out what it is. When the modern humans arrived in Britain and in Sussex about 40,000 years ago, it was populated by large specialised mammals. Giant Irish deer, woolly rhinoceroses, the mammals gradually got larger, from little rodents to large elephants, especially in the African savannah. 3 million years ago, we had left the gorillas and the chimpanzees behind, and eventually gave rise to us. And these very early human-like people could actually make fire, and they could make tools. And that's how we know about them, because their tools last forever, being made of rock. Two million years ago, we have the beginnings of the Ice Age in the Northern Hemisphere, with long, cold, frozen periods which were not very hospitable to life. Modern humans, in the meantime, evolved in Africa about 300,000 years ago.
The only place where life is found. My evolution is a chemical thing. My evolution is a chemical thing.
And it took them another 260,000 years to populate Britain. The modern humans brought rock art and music with them, but the landscape was not empty. For the previous 100,000 years ago, it had been inhabited by the native Europeans, the Neanderthal people. They knew about fire and they were expert hunters. And they were adapted for life in a cold climate. And some people think we all carry Neanderthal genes. The original native Europeans. The tide's coming in now, but in a few hours it'll be going out again. It's run that 60 billion times since the age of chalk.